Hello everyone, welcome to lecture 8 of the course on quantum entanglement and non-local games. So today we look at the rigidity of magic square game. So we have already seen that for CHSH games there was up to a local unitary transformation and up to addition of some extra auxiliary qubits. There is almost a unique strategy for this for winning the CHSH game with optimal probability. Another game which we saw earlier was the magic square game. For this we had seen that classical players could succeed with probability 17/8 at most, and quantum players were able to succeed deterministically. We have already seen one strategy for this, and a question arises that are there other strategies for magic square game which win deterministically? The answer is that no, there is a unique quantum strategy. Of course, we are allowed to perform local unitary transformations, and we are also allowed to add additional auxiliary qubits as we had for CHSH game. So we'll see this result today, and in fact this is the part 1 of the lecture on rigidity of magic square game. We'll follow it up with the second part also. So just to review, so in today's lecture we'll first review the magic square game, and then we are going to see what are some necessary conditions which any quantum strategy must satisfy in order to win this game deterministically. So let's first review the magic square game. So if you recall, in magic square game, the game is defined over 9 variables and 6 constraints. And you can think of these variables as being arranged in a grid of size 3 cross 3 as follows. So we have these 9 variables: v1, v2, v3, v4, v5, v6, v7, v8, v9. These are arranged in this 3 cross 3 grid. And what are the constraints? So these variables are of course vi in 0, 1 for all I between 1 to 9. So these are integers from 1 to 9. And then we have 6 constraints. The first one is that the first row, so this is constraint number 1, that is first row sums to 0 modulo 2. The second row also sums to 0 modulo 2. The third constraint is that the third row sums to 0 modulo 2. And we also have these constraints for columns. Okay, so first 2 columns each sum to 0 mod 2. But then the final constraint on the third column is that it sums to 1 modulo 2. Okay, and here we have Alice's input. So as in usual 2-player non-local games, we have 2 players, Alice and Bob, and the input for Alice is one of these constraints. So it's a constraint index which Alice is provided. So this index lies from 1 to up to 6. So we have this input which is labeled by the variable s, and Bob's input, which is labeled by variable t, is actually a variable index from 1 to 9. So this is essentially a variable index. And what are their outputs? So Alice needs to output assignments of all variables. So these assignments have to be 0, 1 sort of assignments, and so Alice needs to output assignments of all variables in the given row or column. So based on the constraint index which Alice is provided, it needs to assign the variables in the corresponding row or column. And here Bob, who is assigned a variable index, needs to output an assignment for the given variable. Okay. Now, when do they win the game? So, the winning condition is that Alice's output. Okay, here note that when Alice is assigned a constraint, so Bob is assigned a variable index in the same constraint as Alice, right? So, lying in the constraint given to Alice. Okay, so what it means is that, for example, if Alice is given second row, then maybe Bob is given either V4, V5 or V6. So, in addition to the above constraints, the input satisfies the fact that Bob's variable index is one of the variables which lies in Alice's constraint. Okay, so this is the form of the input. And now when we are defining winning condition, so it is that Alice's output agrees with Bob on variable common with Bob. So what it means is that, so here for example, if say Alice is assigned constraint 2 and Bob is assigned the variable V4, so since both of them are outputting the value of V4, so both of them should give a consistent assignment. So it should not be that Alice is saying V4 is 1 and Bob is saying V4 is 0, or even vice versa. So both of them have to give a consistent assignment to the variable V4. And the second, so this is the first condition. So there is an AND of these conditions, right? So both of these must be satisfied. And the second condition is that Alice's outputs satisfy the required constraint, right? So if it's a row, then they must sum to 0. If it's a column, or if it's column 1 or 2, then again they should sum to 0 modulo 2. But if it's the third column, then they should sum up to 1 modulo 2, right? So the parity must be odd for the third column and even for every other row or column. So Alice's output satisfies the constraint. So these are the two necessary conditions, in which case we say that the players are jointly winning the game. Now, the classical success probability, so omega classical of G is at most 17 by 18, right? So this we had seen already. We had also seen that quantum strategy can potentially succeed with probability 1. So this is the optimal probability in quantum, right? And it looks interesting right now, because in one case we can't succeed deterministically, and in the other case we are able to easily succeed deterministically. So we have also seen the strategy for this particular game, right? So let's review the strategy for quantum players. So the strategy is defined as a set of operators, one for each cell of the grid. So there is a binary observable corresponding to each cell of this grid. So the first row, these observables are I tensor Z, Z tensor I, Z tensor Z, and they actually multiply to identity from the first row. Then the product over the second row is X tensor I tensor X, X tensor X, which also product to identity. And in the third row, these observables are X tensor Z, Z tensor X, Y tensor Y, which also product to identity. For columns, the product over first column is identity, over the second column is also identity, but over the third column it's going to be minus identity. And now what's the strategy, right? So these are the observables. So given a constraint, Alice measures the corresponding cells of the constraint, and given a cell index, Bob measures the transpose of the corresponding cell operator. And it turns out that these operators are all kind of symmetric, so their transpose is also the same operator. But yeah, so that's how we define it in general sense. And we have seen that Alice and Bob, they win with probability 1 provided they make these sort of measurements, right? So what is the strategy? So A and B, so firstly they share 2 pairs of EPR. So what's their joint state? Their joint state is given by 1 by root 2 0 0 plus 1 by root 2 1 1. So these are on the first qubits of Alice and Bob, tensored with 1 by root 2 0 0 plus 1 by root 2 1 1, tensored with the second qubits of Alice and Bob. Okay, and given a constraint which could be either a row or a column, Alice measures the corresponding cell of the constraint and given a cell index, Bob measures the transpose of operator in the given cell. Okay, and we have seen that they win deterministically. Note that when we say Alice measures the constraints and it is measuring the cell of all the cells in the given constraint, so these measurements are being performed on the same set of qubits. So Alice only has 2 qubits, and each of these measurements also is a measurement on 2 qubits. So Alice actually makes the same sort, like Alice uses the same state and perform repeated measurements on the same state itself, right? So once a state has collapsed, it uses the collapsed state to perform the next set of measurements, right? So it's not that they are sharing like multiple copies and Alice is going to measure each of the copies differently for each cell of the constraint. So these are the same copies for which Alice needs to make a repeated measurement. So this is one thing. And now coming to the main topic of this lecture. So are there other strategies, right? So these strategies, so this given strategy wins with probability 1. So this we have seen, right? And if you recall the proof, we had seen that for every row the product is identity, for every column except the last one also the product is identity, but the product over the observables in the last column is minus identity. And all these observables in the same row and column, they commute with each other, and so the successive measurements made by Alice on the common state, those are all well defined. And also the product of the cell measurements in the given constraints are all satisfied because the operators themselves satisfy the condition. And we have also seen that via a lemma that since Bob's operators are transpose of Alice's one, so we have psi A tensor B transpose psi. So this is also identity, which means that Alice and Bob, they make the same output corresponding to the common variable, right? So all this we have seen in the previous lectures. So the question now is, are there other strategies? So what is the answer? Well, you might have guessed it. So there are none. So this is also true for the CHSH game, right? So when I say no, that means that up to, so we are defining strategies which are like isometric, so up to local isometries and ancilla qubits. So these operations are allowed, but apart from these there are none. Okay, and so today we'll actually look at some necessary conditions which any winning strategy, deterministically winning strategy for magic square game must satisfy. And in the next lecture we will see that how these necessary conditions which we derive lead us to the unique strategy, okay, which we have already seen, the strategy which we have already seen. So let's start with first finding out what are some interesting necessary conditions. So assume Alice and Bob share an arbitrary state, okay, and this arbitrary state could be entangled in any form, and we are assuming that the state is actually a full Schmidt rank state, psi b, okay, and we assume that Bob's strategy, okay, is to measure a binary observable corresponding to the cell which it is assigned. Okay, so we are assuming that there is a set of binary observable, one for each cell, okay, and Bob has some qubits of his share of states, and based on the binary variable which Bob gets, he is able to make a binary observable measurement. Now in the last lecture we had a discussion, right, that in general when we make the requirement that we are working with full Schmidt rank states, we can't restrict ourselves to binary observables, right, or maybe like projective measurements. We have to move to POVMs, right, but if POVMs only have two possible outputs, we have seen the two outcome POVM lemma, wherein we had seen that it suffices to assume that the measurements are still a mixture of projective operators, and once you have a mixture of projective operators, you can also since it's like a mixture of some strategies, we can also assume that those strategies are all that mixture is giving weight to one of these variables only, and then we can assume that, well, it's actually just a single binary observable corresponding to each input, from which we can actually deduce that these are of the form of measurement of a binary observable, right, because projective measurements and binary observable measurements are all equivalent. Okay, so we did not work with POVM, at least for Bob, but we are also going to make the same assumption for Alice now. Okay, so these all these BIs are binary observables, which means that these are Hermitian and unitary matrices, and they square to identity. And their eigenvalues are of course plus and minus 1. So Bob measures these observable on a state, he obtains plus minus 1, and this plus minus 1 is actually of the form of, so Bob obtains minus 1 or plus 1, and this output I am actually going to interpret it as minus 1 to the power Vj, right. So there is a variable value which Bob needs to output, which is 0 1, but here we are assuming that Bob outputs in the form of minus 1 1. So we have seen this multiple times, that these are equivalent ways to output a binary value, either in the form 0 1 or in the form plus minus 1. So when it's in the form plus minus 1, we assume that it's minus 1 to the power of the binary value. Now another assumption which we are making is that Alice's strategy is to measure each cell of the constraint. So let's say that the constraint index is now S. So Alice's strategy is to measure each cell of this constraint S by a binary observable. So this produces the output which is plus minus 1. Okay, so here actually Alice needs to output 3 bits. So corresponding to each constraints, it has a set of 3 observables which it is going to measure, 3 binary observables. Now here we can't directly use the 2 outcome POVM lemma because its outputs are not 0 or 1, right? So its outputs are 3-bit strings. So these are 8 possible outputs. And the lemma which we discussed earlier was only for 2 possible outputs. So here there is some catch, and I'll encourage you to read the actual paper to see that why we can make this sort of assumption. So for the general case, you should see the paper characterization. So we are not going to discuss the general case, we are only going to just make this assumption that these are binary observables, but for full generality you should read this paper. Characterization of binary constraint systems. This is by Cleve and Mittal. This is from ICALP 2014. Okay. Okay, so we denote Alice's observables by AS J1, AS J2, AS J3. So S is the constraint index and J1, J2, J3 are the variables in the given constraint. Okay. So let's actually write it in the form of a grid. So if Alice is given first row as input, there are 3 such variables and we have 3 such observables, A1 1, A1 2, A1 3. So because we have the variables 1, 2, 3 which lie in the constraint 1. Now if Alice's input is going to be 2, we have A2 4, A2 5 and A2 6. Similarly, if Alice's constraint input is 3, it measures these observables A2 7, A3 7, A3 8 and A3 9. But now if Alice's constraint index is 4, so it measures the first column. So here it measures the entries of the first column and the corresponding observables are A4 1, A4 4, A4 7. Then if the constraint index is 5, these are A5 2, A5 5, A5 8, and then we have A6 3. If the constraint index is 6, then A6 6, because 3, 6 and 9 are the variables in constraint 6. So we have the corresponding observables A6 3, A6 6 and A6 9. Okay, so these are the observables corresponding to Alice. So note that we can't directly invoke 2 outcome POVM lemma here because Alice needs to output 3 bits now, and it is making a measurement on 3 such observables. But yeah, so you'll have to see the paper by Cleve and Mittal to understand like how to deal the general case, when the outcomes are POVMs, not just projective measurements. Now for every j, Alice and Bob return the same output. Therefore, if they are sharing a state psi, then psi ASJ tensored BJ psi equals to 1 for all S and for all J lying in the constraint S. So J is some variable which lies in the constraint S. Then we must have this condition is satisfied for every constraint S and every variable J which lies in the given constraint. And now if you see, we have already seen a result that if you have such a thing which is equal to 1 and psi is a full Schmidt rank, right? So from a lemma which we have seen, that here we must have ASJ equals BJ transpose. Right? So this is the lemma which we discussed in last lecture. And here we are making the assumption that psi is full Schmidt rank. So note an interesting thing, that ASJ is actually independent of S. So it's only dependent on J, it's independent of S. So if we go back and look at Alice's operators, so we have that if you are measuring the observable corresponding to variable 1, whether or not it lies in constraint 1 or it lies in constraint 4, it doesn't matter to me, right? So these have to be equal, these have to be equal, these have to be equal. So actually I could have denoted the Alice's set of observables by just A1, A2, A3, A4, A5, A6 and A7, A8, A9. But to justify why we can do this, we will have to look at this lemma which we did in the last lecture, right? Because so this is the justification that why we can do that. And if I am if I am making the assumption on Alice's set of observables, this also automatically gives me the Bob's observables as A1 transpose, A2 transpose, A3 transpose and so on. Okay, so let me just write it again. So we have Alice's observables and then we have Bob's observables. So Alice's observables are A1, A2, A3, A4, 5, 6, 7, 8, 9, and for Bob I have A1 transpose, A2 transpose, A3 transpose, A4 transpose, A5 transpose, A6 transpose, A7 transpose, A8 transpose, A9 transpose, right? So just from the fact that Alice and Bob have to give a consistent assignment, we have derived a lot, right? So we have proved that Alice's and Bob's variables are transpose of each other, and we have also seen that Alice's observables are independent of the constraint they lie in. They only depend on the variable which Alice is going to measure. Okay, now let's consider the other condition for winning, which is the sort of constraint satisfaction. Okay, so now we are going to impose conditions for satisfying constraint. Okay. So firstly, for constraint 1 to be satisfied, let's say, so we must have that the three outputs which Alice is going to produce, which are like A1, A2, A3, and since these outputs are all -1, 1 valued, so they are of the form their product should be equal to -1 to the power of V1 XOR V2 XOR V3, right? Which must be 1 with probability 1, right? Because the constraint 1, we require that the variables sum to 0 modulo 2 and -1 to the power 0 is 1. And another way to say it is that the expected value of A1, A2, A3 is going to be 1, because these are plus minus 1 valued. So whether the expectation is 1 or whether it is 1 with probability 1, These are two equivalent ways to say the same thing. And this expectation is going to be 1 if psi a1, a2, a3 tensor I psi equals to 1. Now what does this mean? So this means that a1, a2, a3 must be equal to I transpose, which is identity. So Alice's measurements, they correspond to measuring the observables which product to identity. And note that to compute the expected value, I actually took a tensor with I. So this tensor with I is on Bob's system, right? Because when Alice is making the measurements, we are assuming an identity observable on the Bob system, right? And similarly to so basically this is the condition for the first constraint. Similarly for other constraints, for constraint 2 I should get a4, a5, a6 equals to identity. For constraint 3 I should get a7, a8, a9 should be identity. And for columns I will get a1, a4, a7 should be identity. For column 5 similarly I get a2, a5, a8 product to identity. And for column 6 now this is slightly different. Here we will get a3, a6, a9 to be minus identity, right? Because here the variables sum to 1 modulo 2 and then minus 1 to the power 1 is going to be like minus 1. So here what we will see is that here I will get so here I am going to get psi and then minus a3, a6, a9 tensor psi tensor I, then ket psi, this equals 1, right? Because a3, a6, a9 tensor I when sandwiched between ket psi and bra psi, that will give me minus 1. So here actually minus a3, a6, a9 should be identity transpose. So you should work out the details. So this is actually homework to prove this thing. Yeah, it's all like we have already done that, but yeah, just to make it formal I am leaving it as an exercise. And so essentially now we have moved from a binary variable solution to a observable solution, right? So classically if I wanted to satisfy these constraints I should have looked for binary values, but now I can look for binary observables in order to get a quantum solution for these. So in summary, in this lecture we have looked at necessary conditions, to win magic square game. Okay, so what are these conditions? So firstly that Alice and Bob share ket psi, which is a full Schmidt rank state. The second condition is that, okay, so this is not actually a condition, so I'm just labeling it by the number 0. So this is actually not a condition, this is like kind of an assumption which we are making, right? And we are justified in making this assumption. But assuming this assumption, so I'm actually calling constraint 0, okay, because it's actually an assumption. So the first necessary condition is that Alice is observable is independent of constraint index. So it only depends on the variables which Alice is going to measure, right? Bob's observable is transpose of Alice's one for each variable. Third condition, Alice's observables multiply to plus or minus identity depending on which constraint they lie in. And fourth condition is that the observables in same row or column they commute, right? So this is of course necessary for these to be valid observables, otherwise we can't measure them simultaneously. So these are the 4 conditions which we have seen, and then there is this assumption 0 which we have made, that the state is full Schmidt rank. So based on these necessary conditions, we will actually show that the strategy which we have seen is unique. So we will do that in the next lecture, right? So thanks, bye.